welcome to The Explainer. Today, we are diving into a mystery you've absolutely pondered if you've ever been stuck on a long-haul flight. We're going to uncover exactly why those flight maps on the tiny seatback screens look so incredibly strange.
You know the exact feeling. You're settling in for a long trip, you tap the screen in front of you to check the tracker, and instead of a logical straight line from A to B, you see this massive, bizarre curve sweeping way up north before coming back down. Like, why on earth is the plane taking what looks like a gigantic detour?
So here's our roadmap for today. First, why flight paths curve. Second, the great circle secret. Third, locating the vertex. And finally, projecting all of this onto flat maps. Let's kick things off with Section 1, why flight paths curve, the flat map lie. Okay, let's dive right into this. To really understand your flight's route, we have to acknowledge the elephant in the room. The Earth is a 3D sphere, but our screens are flat 2D rectangles. Think about it like trying to peel an orange and pressing the skin completely flat onto a table. It's going to tear and stretch, right? Well, that is essentially what happens when mapmakers flatten a globe into a two-dimensional grid. You literally cannot translate a sphere's physical geometry to a flat surface without distorting reality, especially up near the poles. Think about a standard straight line drawn horizontally across a flat map. It looks like a direct, straight-shot connection, which totally makes intuitive sense, but it's actually a complete illusion. The sweeping curve you see on the tracker is what we call the actual Great Circle route. Sure, it looks like a massive detour on a flat screen, but in three-dimensional reality, that curve is the absolute shortest physical distance across the globe. It literally saves airlines thousands of gallons of jet fuel and cuts hours off your trip. Which brings us to Section 2, the Great Circle secret. Geometry in 3D. So what actually is a great circle route? Basically, it's the absolute shortest distance between any 2 points on a sphere. Because the Earth's surface curves away from you in all directions, a path connecting 2 points on the exact same latitude doesn't just go straight east or west. It actually has to rise toward a maximum latitude, curving up toward the pole to efficiently bridge that gap across the Earth's curvature. And this introduces the real star of our algorithm, the vertex. The vertex is just the single highest latitude point that your route reaches before it starts descending back down to your destination. If you're building map software, finding this one specific highest point mathematically is absolutely crucial. It is the literal key to unlocking the entire perfect curved route. Moving right along to Section 3, locating the vertex, the algorithm. Building this into software is honestly a lot like solving a really satisfying puzzle. First, you find the longitude difference between your start and end points. Then, because of the Earth's perfect symmetry when you're flying between two places at the exact same latitude, your vertex is always going to sit perfectly halfway between them. Step 3, we use spherical trigonometry to figure out exactly how high up that vertex goes. Next, we take those 3D coordinates and convert them into flat 2D screen pixels. And finally, we interpolate intermediate points along the way so the system draws a nice, smooth line. Now, what's really interesting about this math is you don't need to let the trigonometry intimidate you. The underlying logic is actually pretty beautiful. By just taking our starting coordinates and our longitude difference and feeding them into a central distance angle formula, we can pinpoint the exact peak of our curve. With just a few elegant lines of spherical math, mostly just relying on the predictable relationships of sines and cosines, we've got our vertex. Let's ground this in a real-world example. Imagine point A and point B are both sitting right at 37 degrees north. Let's say point A is at 90 degrees east and point B is at 127 degrees east. They're on the exact same latitude line, right? And the longitude difference between them is 37 degrees. Well, following our symmetry rule, the longitude of our vertex is exactly halfway between 90 and 127, so that lands us cleanly at 108.5 degrees east. So, the crucial takeaway here is what happens when we run those numbers through our spherical math. The vertex latitude comes out to roughly 38.28 degrees north. Think about that for a second. Even though both your starting and ending airports are at 37 degrees north, the absolute shortest, most efficient physical path requires the plane to climb over an entire degree of latitude northward before coming back down. That visual detour is actually what shaves the miles off the trip. Finally, Section 4, projecting onto flat maps, drawing the curve. Here is where the map illusion really comes to life. You have to remember, screen coordinates are purely for display. Your computer monitor has absolutely no idea what a sphere is. It literally only understands horizontal x pixels and vertical y pixels. So the map software has to take all of our 3D GPS data, the latitudes and longitudes, and figure out how to project them perfectly flat. And the formula for this is wonderfully straightforward. It simply uses the total image width and height of whatever flat map graphic you're looking at. Your longitude controls your x pixel, meaning your left to right position on the screen, and your latitude controls your y pixel, which is your up and down position. But to actually draw that beautiful, sweeping flight tracker curve, programmers use a really clever trick. You obviously can't just draw one straight line from A to B. And you definitely can't just draw straight lines from A up to the vertex and then down to B. That would just look like a giant unnatural triangle. Instead, the software conceptually calculates dozens, sometimes hundreds of tiny intermediate points all along that spherical arc. It runs every single one of those intermediate points through our conversion formula to get their flat XY screen coordinates, and then connects them all with tiny little line segments. The end result is a perfectly smooth curve with the vertex sitting right at the very top. And this brilliantly illustrates the entire pipeline coming together. The software takes your input coordinates, calculates that 3D vertex, generates all those tiny intermediate points, and then flattens the whole shebang out onto your screen. That process is exactly why a straight line on a flat map is actually a flawed, longer journey, while the generated curve represents the brilliant, mathematically perfect, true path of your aircraft. So we've seen how perfectly this algorithm balances when 2 points share the exact same latitude, using basic symmetry to easily find that halfway point. But it leaves us with a pretty fascinating question to ponder. If this simple elegance works for points on the exact same horizontal line, how wildly complex does this 3D math become if your flight takes off in Tokyo and lands in London? You're crossing entirely different latitudes, which forces the geometry to calculate a shifted, completely asymmetrical vertex. It's wild to think about, and definitely something to keep in mind the next time you're staring at that seatback screen.